Hello everyone, I am Tasbiraha Othoy. Today I am giving a presentation on the optimized operation of weak heaps, operation like WeakHeapify and insert of WeakHeap. And all the algorithm that I will present in this video are from the paper titled Weak Heaps Engineered by the author stated here. So this is a 10 node tree. And when we apply the standard WeakHeapify algorithm, the standard WeakHeapify algorithm mainly construct a weak heap tree. So the main function is the construct function. So when we apply this algorithm, it becomes a weak heap tree as shown here, and the reverse, there is a reverse array to implement in the array implementation of weak heap. So the reverse in the reverse array, the reverse bit are set to ones for these blue nodes, and the small number above the nodes are the actual array indices. So after calling this calling this function, construct function, and constructing a weak heap tree, the rules of the weak heap preserves. So there are three rules of weak heap. The first, you can see in this tree, is that the root of the entire tree has no left child, and except the for the root, the nodes that have at most one child are at the last two levels, and each node stores an element that is smaller than or equal to every element stored in its right subtree. So all the rules preserved. So now, as you can see, it's a standard WeakHeapify algorithm. There are some optimization technique to improve this algorithm. So first is the instruction optimization technique. So in the instruction optimization technique, this distinguished ancestor function is changed, and the distinguished ancestor function becomes like this. Here, observation is that the loop is unnecessary on computers where the position of the least significant one bit can be located using the native primitive operation that counts the number of trailing zeros in a word. So the loop removers, you can see here there is no loop and there is a loop. So the loop remover makes the analysis of this algorithm very straightforward. The distinguished ancestor can be accessed in order 1 worst case time, and for each node, of course except the root node, one element comparison and at most one element swap are performed. The instruction optimization reduces the number of instruction executed. So here you can see there is the operation called trailing zero count. Now I will explain this operation. So trailing zero count, you need to count the number of zeros in a binary representation of a number. So so number of zeros means number of zeros before from the right before occurring 1. So there are two built-in functions to do this. One is the built-in CTZ and another is the built-in pop count. So the example is like that. If you can see the distinguished ancestor, the parameter of distinguished ancestor is index j. So when j is equal to 8, suppose j is equal to 8, then binary of 8 is 1000. So built-in CTJ returns 3 because the trailing zero count is 3, and built-in pop count j returns 1. And the built-in pop count function is modified like this to count the trailing zero so the built-in pop count become bit naught, j bit and j minus 1, this one, to compute the trailing zero count. And then according to the number of trailing zeros, j is right shift to that position plus 1. This is the right shift operation. So how this optimize the instruction is like that. You can see here is in this algorithm there is a trailing zero count, and there is no need for a loop that is doing the bitwise AND operation. Basically the bitwise operation identifies if a number is odd or even, and the trailing zero count and the right shift also do the same. So the trailing zero count the trailing zeros, and the right shift does the function of the return the while loop and return exactly the same number that is returned by this one. In this way, instruction optimization technique takes place. Next, another optimization technique, that is branch optimization technique. So in this branch optimization technique, mainly this join operation is optimized. So in the branch optimization technique, in the instruction optimization technique, the technique already removes the loop used to access the distinguished ancestor. So in accordance, the main body of the algorithm has two unlisted loops that both end with conditional branch. You can see there are two unlisted loop that end with two conditional branch. So but only when stepping out of a loop, a misprediction can occur. Hence, the main issue to guarantee order 1 branch misprediction is to remove the if statement. This is the if statement in the join operation. To do that, we remove the conditional branch. This is the conditional branch, and you can see that in the optimized algorithm there is no conditional branch. So to do that, we remove the conditional branch by using the arithmetic. This is the arithmetic operation which removes the conditional branch. Now the next operation of the weak heap is insertion. In the insertion operation, this algorithm is mainly for repeated instructions. So to insert an element x, we need to, in the array, weak heap array, we need to call this insert method from the construct. The insert method is called, and to it insert x element, it first add x. So to do that, first add x to the next available array entry, and then to reestablish the weak heap ordering, use the shift up operation. Here is the shift up operation. You can see the method is described here. As long as x is smaller than the element at its distinguished ancestor, so join is called and the swap is done. So it need to swap the two as long as x is smaller than the element as its distinguished ancestors. The algorithm need to swap the two using the join operation and repeat for the new location of x. So thus in this way, shift up at location j requires order. So shift up at location j, this requires order log j time. This is the time complexity it requires for the shift up at location j, and it involves at most log 1 plus j element comparisons. When constructing a weak heap using repeated instruction, it is observed that while the execution time increased with n, the number of element comparison stayed constant per element even when n increased. So the total number of element comparison performed while constructing a weak heap using n in a row insertion is at most this, that is 3.5 n plus order log square n. So this is the algorithm for repeated instruction. Now to optimize this algorithm and analyze it in amortized time, there is another algorithm. So what is amortized time? So amortized time is mainly the way to express the time complexity when an algorithm has the worst time complexity, but it's very few time, like once in a while, and beside that the time complexity that happens most of the time. So it can also be marked as average time to complete an operation. Now I will explain the amortized constant time insertion that is done using one buffer weak heap. So the intuition behind the amortized constant time insertion is that the number of nodes that need to be considered almost halves from a level to the next higher level. So the insert is modified so that for any intermediate sequence of operation, the amortized cost of insert is a constant. Here the key idea is to split the element array into two parts. That is, the first subarray contains a weak heap and the second subarray contains a buffer. You can see here. Now the minimum of each of the arrays is at the front of the subarrays, and n denotes the current number of elements in the element array, and if the variable n prime specifies the starting position of the buffer that is used. The buffer size is never larger than log 1 plus n prime. A new element is inserted into the buffer, and if this causes the buffer to exceed its capacity, a bulk insertion is performed by embedding all the elements into the weak heap. So here is the bulk insertion. If no bulk insertion is required and the new element is smaller than the minimum of the buffer, then two elements are swapped and the minimum indicator is updated when there is necessity. So in the now I will go to the bulk insert function, which does the bulk insertion. Weak heap ordering. Here weak heap ordering is re-established in two phases. So this is the first phase. In the first phase, process the nodes level by level. It starts with the parent of the buffer element and perform a shift down operation for each of them, and repeat this until the number of nodes that need to deal with at a level is at most 2. And in the second phase, reestablish the weak heap ordering on the 2 paths from the remaining 2 nodes upward. To do that, identify the distinguished ancestor of the 2 nodes by using distinguished ancestor function, and then perform a shift down operation, and when there is the right node is not equal to 0, and the shift down operation followed by a shift up starting at each of these 2 distinguished ancestors. After the shift up, last shift up operation, that is this one, the weak heap ordering must have been restored everywhere. So now, because the number of elements in the bulk insert process, it is logarithmic, the cost is a constant for per insert operation. So for a repeated insertion, 4n plus order n comparisons are due to the bulk insertion, that is here for this algorithm, and 2n due to the insertion not requiring a bulk insertion. So the total number of comparison for this insert is at most 6n plus order n. And since the minimum indicator gives the location of the overall minimum, so minimum involves no element comparison and completes in order 1 worst case time. So that is all. Thank you everyone for watching.